여보세요, 김 교수님.
네, 교수님 들리시나요?
그래요. 네, 잘 들려요. 얼굴이 안 보이는데, 안 보이나?
아, 지금 켜고 있습니다. 네,
그래요.
컴퓨터가
네.
지금 조그만 컴퓨터를 갖고 와서
어허,
약간 반응이 느린 것 같은데.
어,
네,
오케이. 반갑습니다. 네. Let's get started. We're close to the end of the semester, but we have two more to go. Today we have Professor Joo-hyung Kim from University of Illinois Urbana-Champaign. He's real expert on humanoids. You can ask about everything about robotics and neural network and Gen AI and physical AI to him today. So Professor Kim graduated from SNU. He received all the degrees, bachelor's, master's, and PhD from electrical engineering from our university, and then he spent some time at the Samsung Electronics, and then moved to US. Um, did a I think a postdoc and research at CMU, and then Disney World, etc. So he has a lot of experience, and his entire life was dedicated on creating robots. Now it's yours, Professor Kim.
thank you, Professor. Uh, Hi, I actually had one lecture maybe 2 years ago, 2.5 years ago with this data science department, and probably I have some like overlap slides in this. But what I want to talk about today is there's a huge hype on humanoid robot, which is very unusual to me. I spent over 20, almost 25 years for the humanoid research, but the humanoids was always underdog. So no one was quite interested in humanoid before, except some researchers in Korea and Japan. But now everyone is saying next big thing is humanoid. And my presentation will be more about why people are so interested in humanoids now and which kind of opportunity we have for this research and embodied AI and the physical AI. So, well, Professor actually introduced me pretty well, but I just want to promote my labs, team lab. I'm running Kinetic Intelligent Machine Lab, which is the Kim is my last name, but still Kinetic Intelligent Machine is a robot to me. So I'm running robot lab. We have homepage. Homepage doesn't have much information, but if you are interested in catching up our research, it's better to check our YouTube channel. As Professor Ta introduced, I got my PhD from Seoul National University, and I didn't have much like plan to go abroad, nor to become a professor educator, because I was so into making things. Still, I'm really enjoying making robots. It's much more engineering side up to now. But now many of good companies are actually providing better system than my labs. Well, we are usually doing this one from scratch, but mass production and more money funding will make better system from the companies and other institutes. So I will skip this part. These are the robots I've been building. Most of them are from scratch, but there are some other robots from Boston Dynamics or IIT, Italian Institute of Technology, or Robotics Disney. But most of these are the systems I've been building from scratch. with my team. So these are contents. I will briefly explain what is the humanoid and why people are so interested in humanoids now, and along with the history of the humanoid, and what is the current advance in this humanoid technology, and what are the goal, like well, there is very specific goal market for now. All the humanoid companies are pursuing. So I will explain that part a little bit, and I will explain what is the research opportunities and what I'm doing now. Humanoid is the word itself is actually from Greek. So this OID is actually meaning having the form of the likeness of something. So humanoid itself is literally human-like things. So that's why we are using this word for the artificial, like human-shaped creature. And there are many like similarities from the shape configuration. Humanoid has a head, 2 arms, and 2 legs, and a body. But inside of this humanoid body, the location of the important parts like computers or sensors are slightly different because mostly because we don't have enough technology to make the same functionality with the same form factor, or some other issues like the power system is very different. We are still using batteries for the and the electrical motors. And structure-wise, in the nature, we don't have the revolute joint, which meaning the pin joint, like the most of the robot joint. Human body is using the rolling joint, which is not pin joint. Rolling joint is more like there's a contact of the surface of the one bone and to the other bone. We are using this contact to make the motion between these two segments. So the skeleton itself is different, and the actuation is different. So far, and in the research side, we also need to decide if we wanna have superhuman ability, superhuman capability in this system or not. This is related to ethical issues because of this shape, humanoid shape, people usually think humanoid has similar capability with humans. But let's say we have some kind of X-ray or some other like sensing modality in the humanoid robot, then we can have much more information through this humanoid robot, like much more than what human expect. So that's a very important part when we are considering this one as a commercial product for the public use. So the humanoid, the current definition and the current meaning is much more related to just the shape and the configuration, which is the tree structure of this system. And that's why we are calling this one 인간형 robot in Korea. So why humanoids? This is an interesting analysis for this one. This is not from my slide. There's a really interesting and amazing researcher, Gary Pratt. He had this slide in his presentation. I really like this slide, so I wanted to keep this one. So, well, in Korea, most of people are doing some like personal investment to stock or some other investment. But most of people are trying to hedging the risk, meaning you're distributing the money to different like stocks or different investment categories, right? But Andrew Carnegie once said, put all your eggs in one basket and then watch that basket. So meaning if you are so sure, or if you have really important good information about some target investment, you can actually purchase that. Let's say you can go back to like 10 years ago, then you need to invest to something. Then everyone will purchase Bitcoin or Nvidia stock, right? So it's not exactly same with this, but humanoid robot is only robot we can design and manufacture, support and everything, and can be used in any usage in human environment, because it's a kind of replacement of the human. So if we can make this one really well, then we can just build humanoid robot rather than any other robot. So from this approach, we are talking about general purpose. So general purpose means this humanoid, this robot, can actually go where people go and can do what people do. So for any single application, there is likely a machine that is more optimal than a human form. We are using this kind of devices a lot. Vacuum machine, dishwasher, or laundry machine. We actually cannot beat this kind of devices for cleaning or laundry, right? But general purpose means we can use multiple, we can use the same device for the multiple purpose. So if there are several different applications, a humanoid form is likely close to an optimal single solution style. So last year in GTC, Jensen Huang made this kind of scene. These were fake, not quite fake, but these were displayed. These were not actually robots behind Jensen. And this year, again,
Tell me
Jensen
that
Huang
wasn't amazing.
brought one of the not quite humanoid, but the biped robot on the stage. So why now? Why? So if it's true, if what I said is actually true, then there should be many of humanoid robots before, and there should be some like huge effort to develop the humanoid robot. Right? So actually, in human history, from very old days, like from 8,000 years ago in Egypt, people actually made this kind of structure, human-like structure with some kind of actuation to protect something. In this case, the Egyptian made the one arm with pulley kind of mechanism to raise that arm to protect their tombs. And in Korea, this is not like full body scale, but there's a very small humanoid cave inside Dagyongno, which is the water clock, and that mechanism is amazing. So there are multiple like humanoid kind of shapes for the clock, and the characters are changing over time like that. These are all kinds of this automata kind of approaches are part of humanoids to me, and these are the efforts from old days. In Japan, this is Karakuri. This is amazing mechanism doing very, very delicate like motions like this with only one motor. So it's about 200 like 20 years ago time, and this is very famous. Well, in US, this one is a Lincoln City-10. This one was on air in 1963 when Walt Disney built this animatronics. And at that time, no one actually believed this is artificial devices. So this Lincoln Animatronics is one of the old robot in Disney. In academia, we think the first humanoid robot in academia was developed in 1969 in Waseda University, named as Wabian, and from 70s to 2000, I can say only Japan was very interested in humanoid robot development. No other countries were not that interested in even in US. So all the robots in upper half, those are from the Japan, from Waseda, from Tokyo, or from Honda. And the lower half, these robots are from US, developed by the Leg Lab. Leg Lab was the lab founded by Mark Graeber, who is the founder of the Boston Dynamics. When he was with CMU, he started building one-leg hopper in the 80s, and after he moved to MIT, he started developing bipod robots with his students. From 2000, interestingly, right after Asimov from the Honda was released, lots of research institutes started developing this kind of humanoid robots. And well, current hype is mostly because of the Optimus right bar and from Tesla. But I don't think it's this hype is from it's directly from Elon Musk for sure. But in this community, we've been building all kinds of components for the humanoid development for a while, and the most important event in humanoid history, I believe, was DARPA Robotics Challenge. So after my career with Samsung Electronics, during my Samsung days, I asked Samsung to participate in DARPA Robotics Challenge, but Samsung didn't want to join. So that's why I actually quit the job and then moved to US in 2012. And this DARPA Robotics Challenge is very important because during DARPA Robotics Challenge, researchers and this field community realized, oh, we can actually build this kind of system with current technology. DARPA Robotics Challenge was designed by Gil Pratt, who is the CEO of the Toyota Research Institute now, but he was an MIT professor back in 90s. And he joined DARPA program manager 2009, 2010. And he designed this DARPA program, like the DARPA Robotics Challenge. After DARPA Robotics Challenge, he published a paper, and the title is a Cambrian explosion coming for robotics. Interesting part is that this was published in the American Economic Association journal, not the engineering side, because I didn't know when I first saw this paper, I didn't know much about what is the Cambrian explosion. Cambrian explosion is a period of this uh, Earth. This figure from the Earth. Let me change it. Can I change this? Give me 1 second. From the Earth birth, it's actually showing the history of this Earth, and this is the in the Cambrian explosion. You can see lots of branches are like spawning from here, right? So meaning during this Cambrian explosion, lots of species actually were began to existing in the Earth, and most of them are still surviving on Earth. That's a very interesting part. There are many reasons I heard, but those are not quite. I don't know. No one knows the exact reason, but the what I heard is oxygen level became much higher than previous years, and uh, the creatures could have this vision, not computer vision, the eyes for the vision. So vision made lots of species to survive within some kind of environment on the Earth side. So the title is like this because Gill thought there are interesting 8 technical drivers for the Cambrian explosion in the robotics side. The first one is the computing performance. And the second one is electromechanical design tools and the manufacturing tools, meaning the motor actuator and design tools are much better. And electrical energy storage batteries are much better than previous years, and power efficiency for the electronics. So the power consumption in the chipsets are much better, and wireless digital communication is important, and internet, worldwide data storage, and global computation powers. So from 6, 7, 8. These are very related to current like so-called AI industry, because it's well, first one is also important. Computing performance and internet and data storage and all those kind of things are important for the AI, and other drivers like design tools or batteries. Those are for the much more for the robot agent and the robot design. Anyway, with this said, technical drivers, Gill thought, oh, we will have some kind of Cambrian explosion in the robotics field. And now we have that kind of era. So in 2024, last year, lots of companies released this kind of robots from laptop figure, Boston Dynamics, Tesla, Unitree, Tesla again, Unitree, Boston Dynamics figure. Oh, actually, these are only from 3 companies. But these are all from last year. This year, there are many more data, the videos, but I don't want to have too many videos because uh, at the end of 2023, in the community, we thought, okay, there will be many more humanoid robots for next like 10 to 20 years, and we want to know what will be the next like good platform we can share or we can use for this research. Here's an interesting. Check. How can I remove this line? Sorry. How can I write this? Okay. So this is not totally true because when Boston Dynamics started, they didn't have planned to actually build humanoid robot. They were much more simulation based company when they started. But anyway, from 1992 to their first humanoid robot, they spent over 20 years. In Honda spent 8 years to develop the humanoid robot Asmo from 1993. But from this 2020 era, Tesla spent 15 months to build their first humanoid robot. Well, to release their humanoid robot in public. And Figure spent just 12 months. Within a year, they could actually release their first humanoid robot in public. So now in 2025, if any humanoid company cannot release their first model within 6 months, it will be very hard for them to survive in this market. So Boston Dynamics, Tesla, Figure AI, Agility Robotics, Apptronik, 1X, Sanctuary AI, Unitree Robotics, these are currently kind of like famous humanoid companies in this field. All these companies are targeting, Unitree Robotics is much more for the education or research purpose for now. But all the other companies are targeting the flat floor industrial jobs. Flat floor industrial jobs are as you can see, the Boston Dynamics is working with Hyundai Motors. Tesla is working on the Tesla Gigafactory, and Figure AI is collaborating with BMW and OpenAI. Agility Robotics is working with Amazon, and Apptronik is Benz, and 1X is working with OpenAI. 1X is working on more like home use, but still flat floor environment, and the Sanctuary AI is also working on the manufacturing line in the flat floor industrial jobs. Flat floor industrial jobs meaning it's a huge like warehouse kind of environment without any stairs. Well, some height changes, but mostly flat. And the manufacturing line or logistics. So Agility Robotics is working with Amazon much more just for the logistics, but the car manufacturing lines also have its own logistics within the car manufacturing. If you had a chance to watch Gigafactory inside the Gigafactory with a YouTube video or Hyundai or BMW, all these kind of car factories are already automated up to 90%, 95%-ish. But at the very end of this manufacturing line, you can see many people there to assemble the small parts. Most of parts, those parts are for the human interaction, like the steering wheels or some small handles, or those kind of assembly is very hard for the conventional classic robotic arm can actually make some kind of contribution for the assembly. So to replace that, I don't like this replace the word. To replace that labor, Elon Musk started working on the humanoid robot. But frankly, it's not quite replacement for now because as in US, especially in US, it's very hard to find some good like amount of labor. Labor shortage here in the US is weird. So that's why people think there will be larger market with the humanoid robot in the future. So let's move on to the research topics in the humanoid research. I think it's in most of the audience today is computer science based, probably, right? So
All over the
um,
field.
okay. So optimal control techniques is the model predictive control, or to me, reinforcement learning is also based on the optimal control, just using the real-time update to make the actual like policy more optimal. And the second one is multimodal deep learning for the perception and planning. And the third one is dexterous robotic hand. And fourth one is tactile sensing. And the last one is imitation learning from human demonstration. These are currently very popular topics in the humanoid research. First two topics are more on kind of classic to make the robot do some tests or getting some, well, mostly related to how to solve the test. And the dexterous and the tactile sensing and the human demonstration, just the teleoperation, actually, these are very hot topic in the humanoid research right now. I will briefly introduce this standard process for the biped walking because this is my major from my PhD, and I think this is very important. And this slides, I always have this slide in most of presentation, and probably I had this slide in previous lecture too, but slightly changed it to explain a little bit of details. So biped walking is locomotion is from the footstep planning. When we have goal position and the start position, we need to have this plan for the footsteps. Footsteps can be found with some kind of constraint that is the robot's capability, like stem length or speed or turning angles. With that, we can make this plan with some A-star search or some simple search method to find what will be the next step on the ground. And with this footstep information, we can plan the center of pressure inside the footstep, current footstep. Center of pressure should stay inside the footstep to not to make the robot fall down. So with the footstep plan, we can find good trajectory for the COP within the footstep. So the next part is the interesting part. The humanoid robot is very high dimensional system, and solving the dynamics is very hard. So researchers found some good way to solve the dynamics with simplified model. So if we assume the whole system as one mass, then we can make some kind of inverted pendulum or some template model, low dimensional model, to solve that COM's movement to keep the center of pressure condition, the constraints from the central pressure trajectory from the previous layer, then we can have this purple line, which is the central mass trajectory in 3D using this simplified model. You don't need to understand what's going on here. I just wanted to show what is the process for the motion control. And then with this central, we have 3D motion of central mass and the footstep information with all the timings. Then we can solve inverse kinematics and dynamics to know what will be the motion in the joint level. So we can just use that joint trajectory for the system, for whole body robot. Then the robot will walk if there's no external like uncertainties. During the ARPA Robotics Challenge, researchers found that, we can solve this with most of this optimization techniques in most layers. That was a huge win for the humanoid communities. But what I wanted to show is the dimension of this problem. So meaning, to me, after spending, I don't know, 10 to 15 years, what I found is most of engineering problem is same in the methodology side. What we want to do is we want to find how to encode this issue, encode this problem statement within some space with some mapping, and in that space, the problem dimension or problem is totally solvable formula. Then we can solve that within that space. Then we can expand that solution to the target space for our solution. Meaning, solving whole body dynamics for the humanoid robot. So humanoid robot usually have 30 motors. So for the dynamics, we need to know what is the position of the older joint, what is the velocity of the older joint, and what is the acceleration for the older joint. Already 90 dimensional problem, and there are some other additional dimensions to define what is the origin of this whole system. So usually whole body system, solving whole body system dynamics is over 100 dimensional problem. So to solve that kind of problem with very limited, or we need to design everything, then it's very hard. So the first step, the footstep planning, is finding the footstep location and orientation, the pose on the ground. Just a 12-dimensional space to represent the walking. Then after that, we can find just a center of pressure within that space. Then finding the central mass trajectory in 6-dimensional space. So these are all kind of encoding process to solve this high-dimensional problem in very low-dimensional space first. Then we can make everything work with all this information later. So when I found, well, this is very obvious, and that probably most of researchers in engineering have this same thoughts in different applications. But when I realized this about like 10, 12 years ago, I thought that, okay, maybe we can use like neural net or some machine learning method to just swap this process. That's why I started exploring a little bit of the machine learning method to solve the whole body control issues. Well, this is the Boston Dynamics robot. So you can see, as you can see this video, this one is visualizing the footstep first, then solving the COM motion like that, then robot is moving. This is the robot point of view. So it's actually using pretty similar method I introduced in the previous slide. And this is Tesla, the previous version, Optimus. It's also using the same process. Finding footstep first, then finding the COM movement, and solving the whole body dynamics like this. So most of humanoid robots are using, well, actually use this method. Now, most of humanoid companies are just using RL for the motion. I don't have the slides now, but if I have next lecture sometime later, then I will explain that part. So as you could see the Boston Dynamics video. What robot is seeing is very different from what we are seeing. We can understand what's going on there, but the left video is Tesla autopilot. It's showing the lines and some signals for human to understand what is going on. But internal robot state, it's very unclear to me. We don't need to understand actually. If the robot is working well, then that is fine. But for some safety reasons, we actually need to show this kind of things for human to understand what's going on, right? So I had a chance to ride this huge robot. It's about 4 meter, full body humanoid robot, and the inside, the pilot is actually me. I wanted to show this video. I was wearing GoPro, and this is the inside. And now it's moving. With only vision, well, this is very limited, like field of view, so it's very hard to see anything. I couldn't see even the leg of the robot or arm of the robot with this vision. But it's something like this. If we build the system with limited degree of freedom or some constraint, the world the robot is seeing is very different from what we are expecting. So how to have this some other perception modality, or how to design this perception for the robot is very important for the robot safety and the humans understanding what's going on here. So that's related to the hand and the tactile and the human demonstration. I think these are more interested topics for you too. So I started building some interesting system, plug and play robotic arm system. I think last time I had presentation with data science department, I just introduced this part, but in this slide I have some more contents about how to collect or how to control this data with human demonstration. So plug and play robotic arm system is literally plug and play robotic arm system. I really wanted to deploy more robots to collect more data for different applications. And the robotic arm system is very expensive. So if you want to have up to 2 to 3 kilogram payload with 6 degree of freedom, It's usually like $50,000 and also very heavy. It's usually 15 kilograms, 12 to 15 kilograms. So I decided to develop our own system, uh, which is under 6 kilogram with the same payload up to about 3 kilogram payload, and and can be plugged into some docking mount redesign. That's important part. If we wanna if we wanna deploy this robot to any system, we actually need to have this docking mount everywhere. But we are now using the USB port for the power and communication. So in the future, if there's a standard for the docking mount, I think we can share any kind of robotic arm system or robotic system through that kind of docking mount. So I wanted to spread that idea to this community. This one is just showing the payload. And during last 3-ish years, we developed many applications. So tabletop applications, or we have developed this vacuum machine with the sound, or transform the restaurant serving robot as the mobile manipulator for more capability to move things by itself. And I started to use this test retargeting before everyone used physical AI or embodied AI. No one is using test retargeting, but when I made this slide 3-4 years ago, what I wanted to show was well, with the from the right side, if we have proper configuration, robust like shape for the target test, we already have enough text to solve the test, or videos to solve the test, and converting this information into high level sequence to solve the test to use robots. That's easy. So this is already solved. So this large language models, well, vision language model already solved this issue. So we can easily generate high level sequence in code for the robot. So robotics side, what we need to actually solve is a much more physical interaction between robot system and the target object or target environment, and how to find proper configuration on the right top side. Those are important parts. So these are much more system level side. So my solution is I wanted to use my system plug and play robotic arm system. So we we use our system everywhere. This is my lab, and these are fully automated demo. So robots actually can tell what is the target test based on this location. Then using perception, it can actually do the given task in every location, cleaning and moving things, or helping people to wear the jacket. So this is all like a model based. There's no learning at all. This is a classic robotics research. But what I really wanted to do is from this to solve this kind of all kinds of tasks, I wanted to collect the data, not to use just to use data-driven method. All the engineering solution, the starting point should be the data collection to understand what is the environment and the what would be the possible solutions for this kind of task. And last year, when Jensen Huang brought this slide, I was amazed because this is the project group, the solution for learning how can I say, learning pipeline for the humanoid robot from NVIDIA. So Jensen Huang explained because we have EyeSang, text data, video data, and robot data, we can orchestrate everything for the humanoid robot. Yeah, that's true. EyeSang is a simulation side, so we can generate the augmented data in the simulation, which is very important to know this is test solution is feasible or not, or getting some data through the augmented environment. And everyone knows we have enough text data and the video data for many kinds of tasks and all the kinds of tasks humans are doing, right? But the issue, I didn't like this part, the real robot data. Jensen said, we can just add real robot data from the physical robot. We don't have that. We don't have that because we don't have enough robots at all in the world. So lots of researchers are working on this, the methods, how to collect the real robot data now. And these are the recent works. Most of researchers are trying to use teleoperation, revisiting teleoperation actually. Teleoperation is not new technology at all. So using Apple Vision Pro or using some kinematic chains like the just scaled robotic arm system or motion capture system and everything. Lots of researchers are working on this teleoperation. But there's I think everyone will work on this for a while. Current state-of-the-art method, these are the very recent papers, still tightly coupled to specific configuration and limited support for the force feedback, which is important. We need to add more perception modality to collect this physical body environment data. So we also moved on from the Papra's plug-on and the robotic arm system to robotic limb environment for this modular ecosystem. This is the arms we can attach, introduced in previous slides. And now we have the controller. So controller is, we call this one is now leader and the follower system. So old days we use this kind of system as a master slave system, but because of this history issues even in this technology, even in this robotics field, we are not using master slave anymore. So we call this system as a leader and follower. So this is the leader system for our Papra's, the plug and play robotic arm system. So what our Pebble is doing is with any leader, we can actually control the follower system using our pipeline. Okay. So we can use the same leader devices for the same robotic arms, meaning the configuration itself for the tabletop task or kitchen task or mobile manipulator, we can use the same arms on top of this environment using the same leaders. So Packle is supporting this kind of diverse configurations. And we can also use different leaders, joysticks, or different the leaders with different configuration to control the same follower, same arms, or different arms. So this is the pipeline. I think if you don't have robotics knowledge, it's slightly hard to understand. So from the leaders, we can get the command in joint level or end effector level. End effector is the gripper. So through the kinematic information or VR, so Apple Vision Pro is giving you the wrist joint, human wrist joint pose, position and orientation, and all the finger movement. So we can use that kind of information in our pipeline for the teleoperation. So EEF pose is meaning end effector pose, and or joint position. Using that, we can do task space control or joint space control. So joint space control is sending the joint signal to using the joint signal for the control. Task space control is end effector control. And using some robotics knowledge and the model, we can solve the inverse kinematics, and then we need to have some kind of safety filtering. It's not just a low pass filter kind of filtering to check if there's any collision we are expecting from the model and the environment. We can block all those kind of area using the model. Then or there's some other safety filtering based on the robot's capability. So if the leader operator is moving too fast, then we need to send a little slower command to the robot for the robot safety. From this command, we can send all the commands to the follower, the robots, target robots in real world or through the ROS 1 and ROS 2 or simulation. We are supporting Mujoko or Isaacsim or Gazebo, and these are most popular simulators in the robotics field. Then feedbacks from the robot side, we can get the follower state for the intrinsic feedback and the extrinsic feedback for the user to feel what's going on through the system. It's not just by seeing seen by users, seen by operators. Through the system, we can actually give feedback if there's kinematic body in the leader side. We cannot give any feedback to VR because VR doesn't have any physical interaction between human and human manipulation and the system. But we can give this kind of feedback through the joysticks or this leaders for the robots. So intrinsic feedback is when we have more than 6 degrees of freedom, then 6 degrees of freedom is in the robotics is a position XYZ and the orientation XYZ directional rotation is the representation for any rigid body. So if we have more than 6 degrees of freedom, there's a redundancy. So redundancy will make some issues in controlling this kind of system. So let's say we have 100 degrees of freedom, 100 like zone in one system, then that shape of the system will be will act like some kind of deformable like rope, right? If it's a very high dimensional system. So if there's any redundancy, if there's any like pre-tensioned force, that shape will be like acting, moving like free motion. So to avoid that, in the leader side, we made some kind of path to add virtual force in the leader side for the operators. And extrinsic feedback is when there is any difference between the target, the commanded uh, input to the robot side and the actual robot in simulation or real world, we can get that feedback through the system for the operator to feel there's a difference in the actual robot side. So here, in the video, the gripper is already closed, but the follower side, robot arm side, the gripper is moving slow, so it's not closed yet. Or in the video, as you can see, there is a cup, right? Because of cup, it cannot be closed. So in this kind of case, we can give feedback to the leader side, so operator can feel there's some kind of object. So this is very simple and straightforward, but having this kind of force information in this teleoperation system is not easy. So adding this kind of force level modality into the physical system for the teleoperation, that's a very important part, and everyone is working on this. And when the leader and the follower has different configuration, it's a little bit hard to see, but the leader, the control part, the configuration is different from the follower. So we can add this force feedback in this kind of case through our new pipeline. I will move a little bit fast. I think that's time is already our. So I can show you what is the leader side and how we can collect the data through this kind of test. So this is the DRM manipulation through the teleoperation. And if you are interested in the robotics side or physical AI, you probably saw the PI, the physical intelligence video. They are collecting this kind of data a lot using their own system. And I've been talking with them about the teleoperation system a lot, and I know what is the current needs in that kind of industry. So how to use different data in the leader side for the robot is important. That's why we made this a diverse different data set, different representation for the motion side, to control the robot. This is the important part for the data collection for now. And oh, oops, sorry. This one is showing the operator is wearing. Why this one is not working? Wait a second. Uh-oh. Uh, my computer is kind of frozen now. Give me 1 second. Do you hear me?
Yes.
Uh, my computer
So
is frozen now somehow.
okay.
Uh, while I'm working on this, I can guess some questions. I oh,
Oh.
uh-oh.
PowerPoint, yeah.
Yeah, I think it will take a couple of minutes. So if there's any question, I can get some questions while
Yeah, I
here.
think
Okay, yeah,
so. Maybe I think it's getting close to the end of uh, the seminar.
right,
So,
right.
any questions? This is an excellent talk, covering a lot of things, also a very friendly introduction to humanoid.
Thank you. Okay, are you seeing this video now?
Yes,
Okay, so this is the Apple Vision Pro interface. So this is the real time when the operator is squeezing the end effector is actually trying to the parallel gripper is actually closing for the manipulation. And so for the pop arm, we can have different configuration for the operator to control this right next to the robot system. Or we have now we have two kitchen settings, so operator actually can see what is the well can just imagine what is the environment with the same setting like that. And this is new device using the baby carrier to control the humanoid robot. So most of parents, I think, have that experience to move their babies uh, in the baby carrier to mimic some kind of motion. So we can actually collect the data through this kind of device right next to the robot for the teleoperation. And the latency is pretty okay, so we can do very reactive motion using the system. And also can use this one for the different configuration like this. So, well, you probably most of you are interested in what is the data like. So for the vision action model for now, in robotics field, the people are using one external camera the, to see the test space and the two, well, one camera per gripper. So for the dual manipulator, we are using two cameras like that. And this is the data like. So for the vision action model, it's very important to um, make uh, store this data as a reusable form. So that's why we denote the background using the depth. camera for the training. And this is the transformer-based so-called vision action model. So we collected for just to do this simple task, grasping the Pringles cup and moving that on into the basket. We collected 250 successful episodes using the teleoperation. And on the video, right video, you can see some blue and green lines. That is the result of the policy. It's actually showing the next, I cannot remember the numbers, but the based on the current state, it's meaning current state of this robot joint and vision is generating the next trajectory of the grippers to solve this task. So I found this is interesting, but still very heavy, and in my point of view. And it has very interesting failure-safe solution. It's meaning if we want to use model-based control, and if we want to check what is this current state is failure or not, we actually need to have to make some kind of failure evaluation or some kind of if-and case, lots of if-and case to rerun the task when there's any failure. But the transformer-based, we also use the diffusion model too, but this generative model-based approach is interesting because when there's any failure, it's not quite failure to this method because it's only generating the next trajectories based on the current state. So if the Pringles is dropped, then that's the current state, and the robot is doing something based on that state. It's not, we don't need to have any failure mode to overcome that kind of failure. That was interesting, but still it's very clumsy to me. And collecting 250 episodes, successful episode is painful just to do this kind of test. So how to collect more data is very important. I think I am going to skip this part because it's more about the tactile sensing we are developing on top of this our system, or the dexterous hand to collect more data, including the tactiles. So if you are interested in this kind of thing, you can check our YouTube channel and the papers. So I really wanna get some questions. So I wanna just close my talk. In this presentation, I briefly explain what is the humanoid robot and what is the history and why people are so interested in humanoid robot now, and what are the opportunities in the humanoid research. Okay, that's it.
Okay, thank you very much for really friendly introduction to humanoid. So I think even those who do not understand the mechanical engineering can understand what are important in this research. Any questions from the audience? Can I ask the one question about what can you share any information about what this NVIDIA and World Labs, Pepe Lee's World Labs, these companies are doing at the moment? What's the current state of art, and what kind of an environment do we need to build to do the competitive research?
So, that's a good question. I don't know what will be the competitive research, but I know what is the intention of the NVIDIA for sure. Because when machine learning became very hot back in like well, almost 10 years ago, NVIDIA was spending some time to develop the software pipeline and everything. And they said that they will support this community because of, but after some time, after some other tools like PyTorch and other stuff came out in the world, NVIDIA started not to develop those kind of tools and focusing on they just focused on developing better GPU, right? So meaning um, in my presentation, what I showed is in the humanoid side, what are the like tools to collect more data, right? So meaning there will be much more high dimensional data we need to deal with, and NVIDIA is seeing that part. So
Mhm.
for the humanoid industry, we are currently using at least two computers in the system. So one agent is holding at least one or two CPU and one GPU. So, and what I said was we need much more robust to collect the data, meaning we will need much more GPU in the agent side. But after that, after we deploy lots of robots, there will be tons of data through that system. So that data, that amount of data is it. NVIDIA is NVIDIA is free market for that data. So NVIDIA is focusing on the humanoid robot for now to encourage people to spend more time and efforts to develop this kind of system. But they will, in my opinion, they will focus on system integration a little bit later, or like small form factor GPU for this kind of mobile system. So they can keep their servers and everything. Well, they can sell more GPUs later.
Mm. I guess the data management here becomes very important. You
Right,
know,
right.
So I don't know what kind of infrastructure they use. Probably they use file systems, and then they may not be able to manage this kind of. I mean, the structure is changing. The content is changing. So there's a serious data management issue here.
Right. So, yeah, that's very important point. So the current problem I wanted to show is through this slide is actually related to the data representation of in the
Mm,
robotics field. So for now, people are using just raw data, collecting, saving all the data through the system, which is not efficient at all. But the problem in robotics field is we don't have good data representation for now because we
mhm.
are using all the different kind of robots and we don't know what is the good data like format for for this kind of task yet. So that's important part. But some company like Hugging Face think
Mm,
how this kind of data will be important later, even before we can we find the data representation. That's why they are